So today I will gonna talk about my previous results about copper zinc binary clusters and nickel gallium. The first part will be about nickel gallium results, and the second one about copper zinc is very fresh results, but I have some information to support to you today. Okay, now I'm just finished my postdoctoral here in Professor Juarez Group. It's a pleasure to come back and have some conversation with you. Please self yourself, be comfortable to interrupt myself and make some questions, no problem at all. So initially about the naked cluster for nickel gallium binary clusters, we start with M13 and N14 systems with three different stoichiometry systems for nickel 6 gallium 7, nickel 7 gallium 6, and nickel 7 gallium 7. So we have basically this kind of structure by experimental results, and we can separate the different regions on the clusters. So we just exchange the sites of nickel and gallium and re-optimize the systems to try to understand how the potential energy surface behavior between this kind of exchange. It's important to remember that we use this kind of conformations and ab initio set of configurations to do this structural set mapping. This initial framework here is provided by Maxi by XRD experiments. So this that the picture is provided by experimental data. Okay. However, just these regions are our understanding about the symmetry of the clusters. Further, these experimental results, we improved the structural set with pure ab initio calculations to like a Bayesian Hop Monte Carlo and tree growth approach. Okay, so initially we obtain this kind of relative energy surface. Okay, and we can see that for M14 nickel gallium, nickel 7 gallium 7, we will reach the lowest energy configuration with the gallium atoms on the outermost sides of the clusters. And as we up the energy, the nickel atoms go outside of the clusters. Basically, we can observe this kind of behavior on M14, M13, and nickel 6 gallium 7 and nickel and the nickel 6 gallium 7 too. Okay, basically here we have the gallium on the outermost sides of the cluster and the nickel to the inner sphere of the cluster. This is for the naked cluster. However, when we put the ligands surrounded, the behavior of this kind of cluster totally exchange to a system like that. Here we show the M14 cluster results or mapping that we have done. So now we can reach some minimal configuration structure with nickel on the outermost sides of the clusters, performing a binding between the cluster and the ligands. Okay, we can observe the same behavior to the M14, N13 nickel 6 gallium 7, and N13 nickel 7 gallium 6. One interesting thing here is that if you show, I don't know, it's here, the previous slide, M14 here, this system here, we can observe a kind of gallium atom on the outermost sides performing a binding with the ligand. However, it's a very small picture here, but we already have performed some different approaches that the gallium atom, this kind of configurations it starts to broke the symmetry of the cluster, and probably it is not a suitable configuration from DFT calculation. So basically, in this previous studies, our calculations match very well with the experimental results, and we can tell a little bit more about the properties of the clusters. These properties, one of these properties is the PDOS. Probably the most important one is the PDOS of this kind of clusters. For N14 nickel 7 gallium 7, we have homolumo gap of 0.242 electron volts. So for nickel 6 gallium 7, this homolumo gap is about 0.136 electron volts. And the most interesting thing here is from nickel 7 gallium 7. The homolumo gap is very near from each other, about 0.066, and we have the appearance of a new peak on PDOS here, built mainly by the nickel and gallium orbitals. Okay, and this PDOS can suggest the behavior, the completely different behavior on catalysis for nickel 7 gallium 6. This is important because exclusively on this kind of system, we have a free nickel atom on the surface, free to binding nickel atom on the surface of the cluster. So we already start to do some calculations about the hydrogen molecule adsorption here, just comparing the different, the same site of adsorption for nickel 7 gallium 6 and nickel 6 gallium 7. These calculations is almost finished, but not yet. We can discuss it probably, I don't know, today morning. I just take a look there, not finished yet. So we have now 8 steps. Yeah, it's more or less we are spending 5 or 6 hours to do one step or geometry optimizations on our cluster or our local cluster. But this problem can be solved with when Santos-Dumont just start to work again. So this is not a big problem. Okay. The highlights, it's basically on the nickel gallium clusters, naked clusters, the structures are very dependent of the locations of gallium and nickel. We can completely destroy the symmetry of the systems just exchanging the positions of nickel and gallium. Another point, on the naked clusters, the gallium prefer the outermost sides of the clusters. However, on the coordinated systems, we totally exchange this behavior of gallium. So in the coordinated clusters, we have nickel on the outermost sides and gallium on the inner sides, and nickel performing the coordinations of the CP star ligands. So nickel atoms preferentially the outermost sides. We can, using your in-house method to perform the conformational set achievement, we can reach the same minima as the experimental data. This is a very important thing because it can validate our method to see what happens with these clusters. And as we show in PDOS, probably, sorry about the letters here, is not as small as one, but nickel 7 gallium 6 coordinated clusters probably have a completely different catalysis behavior. So initially we perform the PDOS, we are performing another kind of just adsorption of one molecule of hydrogen. So we have to wait and see what happens now. So now I just finished to the calculations about copper and zinc binary clusters. We start calculation 4 different metal clusters. So these initial configurations are provided by X-ray, provided by Max Schultz here. And we have the system copper zinc 10 with 7 CP star ligands, copper 10 zinc 2 with 2 CP star ligands and 6 mesitylene, is that right? Mesitylene ligands. So the copper 5 zinc 8 with in copper 5 zinc 9 with 8 CP star ligands. Basically, these were the experimental structures that were provided for us. So we have basically the copper atoms on the inner sides. So as here, 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 and here. So we just performing now the exchange of these positions, retaining the stoichiometry. Okay, as can I explain here the most easily way. Basically, what we done is just exchange this central atom by this. Just do an exchange copper here by zinc and zinc by copper. You retain the stoichiometry and perform the optimization calculations and see what happens about the energy. Please, Naido. Of course, the stoichiometry probably will change a lot the energy because you have different chemical species. However, we can calculate if has some doubts about the different stoichiometry region or stoichiometry balance. We can do some kind of excess energy. So to reach the perfect moisture of copper and zinc. However, for these initial results or initial point of view, we didn't perform it yet. It's possible we can do it. However, in these previous results, is not done yet. Okay, we have to figure out if it's possible to do the better manner, and if we're gonna look at this. Okay, it's all right. Okay. Yeah. Yeah, yeah. We can perform this exchange by symmetry in chemical behavior or chemical environment on the molecule. Okay, there is no. It's a kind of. It's a kind of the same if you perform the change, the exchange, this atom here or this. Yeah. The second one here. Here. Okay, here. Yeah, however, here and here is completely different because this is a kind of bridge between the central atom and a binding metal atom. So we try to reach this kind of conformation. You will see in the next slide here that I show the relative energy surface. So we can see that the experimental conformation here with copper atom on the center of the clusters match with the lowest energy configuration. However, with start, if we start to exchange the copper atom to the othermost sides, the energy starts to rise. Okay, so the higher energy will be with the copper performing the ligand binding at the different ways, of course, because we have a non-totally symmetric cluster. However, we try to reach all the possibilities in the simplest way. This, uh, this can be performed by hand. You can exchange using your mind. or you can perform it randomically and try to separate the identities of these clusters. Okay, to for this is not so useful because you have just one atom, you can exchange, it's okay, you can see the symmetry, perfect. However, how can you reach a lot of confirmations with you have two atoms to get to exchange in a system like this, 12 atoms? So we performed to a kind of identities classification before start the calculation. So we can perform a kind of exchange randomically the atoms, and after this apply Euclidean metrics to provide the identities. And after this, we have more or less sure that we can uh, scan all the potential energy, probably at least a good one. An indicative that we can that these results are more or less good. That here we have the zinc atoms performing the binding with CP in here, and here we have the CP, the zinc atoms doesn't perform any binding with ligands. It's a complete opposite way between this kind of molecules. And here we have the highest energy, and here the lowest, and a kind of sigmoidal, I think, behavior between the two of these configurations. Probably because the uh, probably we can measure the interaction energy between zinc and CP star, and the interaction between copper and CP star in this case. Furthermore, the copper probably has a lower radius, so it can be easily fitted on the inner sides of the clusters. Yeah, it is a kind of preliminary results. I know that we have to perform more, extract more information to a paper, but it's just a previous results. Yeah. No, this case, we just perform calculations to the binding with the protected clusters. Yeah, because more or less we are most interested to solve the experimental problem pointedly. Okay. Yeah, 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 yeah. I agree. I agree. Yeah. However, it's a kind of we have to perform fast and fast calculation to solve the problem the most faster way. So yeah, I agree with you. But you, yeah, yeah, yeah.
I suppose that the answer for what Juarez was asking lies partially on what Max was saying. of the orbital filling, the orbital filling, and furthermore, you could explore, I think, in more detail, the interaction between the zinc and the CP star. Is that CP star? I think you should not find a very great charge transfer between those species because I think essentially the interaction lies on a hybridization change, so you might find some covalent interactions. I think you should explore in more detail to get answers for for a paper.
Of course. Thank you. Of course. Yeah, 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 yeah. Okay, okay, okay. So until here, everything is all right. Our calculations are matching with the results of the experimental guys. So now starts a kind of different conversation. Here we provide we perform the same kind of exchange by positions on the atoms here, and we can find that the experimental structure here pointed it's the different is different from the lowest energy configuration proved no, achieved by DFT. The the behavior is more or less the same. We have the copper atoms on the inner sphere of the cluster. However, in the lowest energy configuration, we have a kind of more segregated between copper and zinc. The copper tends to uh, stays near from each other, and the ligand binding is performed by zinc atoms. I agree, we have a lot to do between the electronic behavior, the structure, the binding energies to how can I say how can I say it by to provide a solid information. Yeah.
You're using any other walls correction for this calculation?
No.
Have you tried to make a conversion? It changes a lot the relative energies between using and not
We try it on another class of clusters of by 55 atoms. I performed some tests. Usually the binding energy doesn't change any too much, and uh, the, 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 the trend, the surface is still the same for 55 atoms. Okay, so I just exchange my subtract and uh, take as take it as a true. So basically, is that. For the 55, we perform with or without ligands. We performed this test a lot of time ago. Yeah. Hmm. Yeah, yeah, of course. Yeah, we should to check. However, this the second the preview the next slide the calculations just ended I think on Friday last Friday. So it's very fresh results, and we have to go further, go more deep. Yeah, but of course, the homolum gap it's a kind of number that we can extract easily. Okay. Yeah, 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 yeah. And the last one here we have once again about 10 structures below in energy from the experimental uh, uh, provided structure. The same way, we can find copper segregate region here on the center of the cluster. So we will perform more analysis, but the important thing is that the time consumption more time consumption part is done until now. So about the highlights, our method can reach the same uh, uh, minimal structures for copper zinc 10 and copper 10 zinc 2. However, as we expect, I guess, because the resolution of the X-ray diffraction uh, spectra is not very well resolved, but the copper 5 zinc 8 and copper 5 zinc 9, we can reach better not, but lower energy configuration using our DF3 approach. So and at least the zinc atoms preferentially go outside of the clusters, performing the binding with CP stars, CP star more easily. Okay, so that's what I want to show to you today. I want to thank you all, and I'm open to get questions. No, no, it's all free to relax. All free to relax. It's important because we already observe in the case of nickel gallium that the freeze of clusters can like a bias some different uh, different phenomena like break the symmetry of the central cluster. That's why we keep all free to relax. Okay. No, no, we use, oh, sorry, it's not on the presentation, but all these calculations were performed in FHIMs using light year 2 basis function, okay?
As we were discussing before, Juarez told about the binding energies, but you have to see the binding mechanisms uh, from the naked cluster with cage through the states that arise from this interaction. So one thing that you could do is to perform the PEDOS with the naked cluster and with the distortion structure to see what states are appearing there, because then you can have a clue of what states are dominating the interactions that you have between your cluster and your CP star. So you define the binding mechanism.
Even to define the binding mechanism, I think, I guess that the most properly structured is to take the single point from each configuration. That's yeah. And after you can do a lot of another preposition like PDOS, charts, and so on and go on. Yeah. Yeah, exactly. The binding states is depending on the each structure. No, not yet. As I told, it's freshly results, and I have a lot to do yet. So, but I think that the most consumption time part just gone. So, yeah, 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 yeah. Of course. Let's wait for the experimental guys. What you do, what you have, what you want for us now. Yeah, yeah. Thank you, Nigel, again. Now this position is fixed because we start. Yeah, the important question here, but we start with this kind of configuration. This is from XRD spectra, okay, and we just exchange the metal atom sites, just it, okay. But after this, we exchange, start a new optimizations from this point, okay. No, 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 no. No, we didn't perform it yet. So I think I don't know, but uh, I saw the CIF files. Okay, there is some mismatching between the stoichiometry. However, the position of the ligands are very well defined. So we have very well defined position of each metal atom. We don't know who is or what is the atom, and we have very well definition on the position of the ligand. Okay. Yeah, this is. Yeah, it's no, it's pretty similar. It's pretty. Yeah, I just I did some previous look at. I don't have the number, but we can achieve this number, okay? And after this previous look, we can see very few atom displacement, but with very small displacement here. Okay, it's more or less in between this is in this between this. Yeah, it's very. Yeah, we can. Yeah, we can do it. I think we can do it about using the Hungarian method that calculates the RMSD between the two structures. I think we can use it. Yeah, it's a kind of easy number to obtain. Hmm. I think one important question that you did to me yesterday about which is the preferential composition, the stoichiometry, uh, copper 5 zinc 9 or zinc 8. We can perform some treatments to try to find the stabilization energies. Yeah, we will perform and we will. Yeah, I don't. I don't have the numbers, so I prefer to stay calm and we can figure out. But yeah, it just change one atom more in this cluster here than this. And one problem, a calculation problem that I faced. If you see here, we can see a lot. We can see 24 points on our potential energy, relative energy surface. Here, I have just 15. So why? First, uh, all the calculations were the initial sets is more or less the same, but not all the calculations have finished yet. We face a lot of problems on the algorithm of optimization here than the previous results here. So uh, we have a lot of way to walk here yet. Yeah, 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 yeah. Yeah, yeah, yeah. So it's all right. Basically, the difference, I don't know. Here, you can see here, Professor, we have two atoms binding with the same CP stars. It's hard to see here, sorry, but it's a problem. It's a yeah, but this is the basically difference between the two complex.